Okay, so just a last minute addition to the agenda. Okay, Jason has gone away from the States. Very cool of me and guys didn't let him have a set slide, although he's last minute. So we're just going to give him 10 minutes just to show him what he's doing over there because he's very relevant. This morning. Yeah. So over to Jason, and then we'll crack on after Jason.
Okay, thanks so much. Sorry, guys, for occupying your time for coffee. It's about last minute to share my PhD research. So I realized it was not clear my approach, which I want to share with you. Especially some presentation mentioned that solar gas, solar radiation is very important. And that's my PhD research. So I want to share more with you. The title is In-situ Data Driver Estimation of Dynamic Solar Gain in Buildings. So it's mainly about how to use data to quantify the dynamic solar gain. A little bit about myself. So I did my PhD at KU and then I moved to Enschede at the University of Pennsylvania for my postdoc. And luckily, I got my tenure track assistant professor position last year, and I have worked there for 1 year. So I will at least stay there for another 5 years for my tenure track. By the way, Arizona is very hot climate, so that's a good location to do the cooling driver, like data analysis. And by the way, staff and Drake is my PhD supervisor. My PhD supervisor, and I work at IEA next 71 PhD. So okay, let's talk about my PhD research. Again, this is the title, and you will see some keywords about data-driven, solar GAN, and gray box, and AIX modeling. So there are 2 types of model. And this is my PhD thesis. Actually, you can download online to search this. Yeah, let's talk about what's a solar GAN. I think most of you know it, so I just quickly go through it. And it's a important part of the the energy GAN. You provide the energy balance equation, and how to quantify the dynamic solar GAN is a problem. There are 2 typical ways to do that. One is the direct measurement. One is the right box simulation. However, both of them have drawbacks. For example, if we measure the solar GAN, at least the indirect part couldn't be measured. Yeah. And if we want to do a simulation, it's possible, but you need a lot of data. That's why, for example, for the DOE prototype building, it's very simplified. If you compare to the reality, for example, the self-shading, for example, the shading for the nearby building is how to measure, especially for the trees. So both approaches possible, but they are not efficient enough. That's why in the Annex 71, we use the data-driven approach to fix this problem. Then a quick slide about what's the difference between black box and the gray box model. So maybe most of you know it. So the gray box model is a combination of the white box and the black box. So it can have the existing equation from the physical knowledge, and it also can have some data fitting method to estimate the parameter, which is unknown when you write the equation. For example, this is a simple case of how the gray box model look like. It's RC model, and you will write the system equation. So on the top is system equation, and you will see a color code. The blue code means the input data, and the red code refers to unknown parameters, which means a lot of data, a lot of parameters are unknown if you write the equation and when you establish the model. So then there's a problem. If we take a look at the solar GAN is here, and we will write as the solar GAN coefficient, J value, multiplied with the global horizontal irradiation. So you can see it's red color, which means we don't know the value of the J, don't know the solar GAN coefficient at this moment. Then we have to assume it's a fixed number. That's why it might lead to a problem. For example, for this case, we have it's very popular for this type of house, at least in Europe. So for this case, it only has the window on the east and west side. So which means it only has solar GAN in the morning, early morning, and late afternoon. Which means, again, if there's no solar GAN, there's no solar GAN distribution. So the solar gain coefficient should look like the blue curve. A peak value at the beginning and another peak value in the late afternoon. But it will force it to a fixed amount, fixed value. It will be horizontal line. So let's see what will happen. And that's a typical curve of global horizontal irradiation, right? In a sunny day, on a sunny day, by the way. So it will, if you multiply this value with this curve, and then you will get the estimation of solar gain with two patterns. The first pattern is reality. So it will have a almost zero solar gain during the noon time when there's no window available for the solar radiation. And this is the estimation of the solar gain when we have a fixed solar J value. Hope this clear. So the assumption of the fixed or the stable or like constant solar gain coefficient might lead to some problem, especially when the building have evenly distributed windows. And the problem is how can we have this curve, the blue curve, when we have limited data? So that's the problem I need to solve during my PhD. So I made it work, by the way. So you will see I proposed two type of model. So you can see this line always. So this line integrate the gray box model, and this one integrate AX model, and all the presentations are reviewed in the paper recently published. So this is the B-spline fitting, by the way. So it can use the pre-constructed B-spline with weighting factor, something up, and get this main train of this curve. So we will use this technique to estimate this curve to represent the solar gain coefficient, dynamic solar gain coefficient. And there are the papers, and this is the review paper. Yeah, so let's take it one more time. So this is the pre-constructed B-splines. And we have the weighting factor to make some a little bigger or a little bit smaller. So when they sum them up, you will get this black curve. And very interesting is this is a non-linear relationship, but if you take a look at the equation there, it seems like a linear regression. So we use the component of pre-construct B-spline to replace here and transfer the non-linear dynamic into a linear regression. So about the result, and you can see I did some like test based on this prototype building. And first, starting from the PRBS signal with the 1 zoom zoom, and then I add shading devices to make two scenarios. One with 4 windows, one with only 2 windows on the east and the western side, and also collect weather data from the weather station not far from there. And you can take a look at for this winter data set, we have 4 windows. And you can see this is the analysis of the path of the sun. So you can see the peak value should be somewhere around early morning. So you can see it reflects the dynamic. And if we change into the summer data set with 2 shading devices to shade the southern windows, so which means we only have 2 effective windows on the eastern and western side. And then the curve changed. So you can see the peak disappeared here. So you can either disappear. And then I tested this model into 2 thermal zooms. So you can see this is 1 thermal zoom and there are 2 thermal zooms. And then changed the heating pattern into a more realistic one. We made some assumption to assume there are 2 people living in and with different daily pattern and have some like heating power to imitate this and the heat gain from the occupants. Then you can see again, we only test the second scenario, so you can see it will also reflect. Yeah, it's over there. There's something very interesting. The orange curve refers to simulation, and you can see a big gap between the simulation and the data-driven modeling. And actually, based on my analysis, it's based on there's a tree I didn't model in the simulation. That's again linked to what I mentioned at the beginning. Okay, so let's talk about HLC now. We're talking about the solar gain. So this is another paper talking about if we have a better model to quantify the dynamic solar gain, what's the performance of this model in HLC determination? So you can see they're almost the same. It's very similar. And most importantly, it can reflect the summer and winter. You can see the summer is always a little bit higher than the winter. This original zoom and this blue zoom. So which means this model can not only do a better job in quantify dynamic solar gain, but also do a good job in HRC determination. So thank you for your listening.
We have got time for one question for Jason.
Yeah.
Any questions?
Any questions?
Good job then.
Thank you so much. Thank you for opening this
I
opportunity.
imagine it's very useful where you currently are as well in Arizona.
Okay.
That's great. Thank you.
Thank you.
Okay. Slides us.
Yeah.
We've just got this working. What's the transfer machine at this point in the day?
If I just show the TV,
Yeah.